Hi guys, it's Ms. Caspero. We are discussing continuity of functions today. To define continuity, you first define discontinuity. You can't trace the graph without lifting your pencil. These are defined on the next slide, but I'll keep looking back at the graphs while you're getting these definitions. Infinite discontinuity. It means that these are forever separated. Okay? There's always going to be, it's infinite discontinuity, you're always going to have something called an asymptote. It can get close to it, it could just never touch it. But that's where you get that infinite discontinuity. Jump discontinuity. It approaches a different value when you're coming in from this side than it does coming in from this side. That's approaching from the left, approaching from the right, but we come up with a different value. That produces jump discontinuity. Point discontinuity, right here, is when you have a rational function, and what happens is this x squared minus 1 can actually be factored into x minus 1 times x plus 1 over the x plus 1. So these x plus 1's match up and can be canceled out, and so you end up with just a basic little x minus 1 line. The problem is the original function was a rational function. That domain restriction is still there. X cannot equal -1 because it would make the original function undefined. So at that point, it is discontinuous. It has a discontinuity. They call it point discontinuity. It is also called a removable discontinuity because it can be removed in later iterations of the function. Okay. Here are your types of discontinuity. Everywhere discontinuous. It's impossible to graph in the real number system. For example, you got 1 if x is rational and -1 if x is irrational. You would never be able to graph that forever. So that's everywhere discontinuous. This is what gets you because it's infinite discontinuity here. That is where you have the value of the absolute value becomes greater and greater as x approaches a given value. That is also, like I said, where it has an asymptote. That's what you're looking for there, an asymptote. Jump discontinuity. The graph jumps from one y value to another at the same x value. That's usually what we were dealing with piecewise. Occasionally they would overlap, but mostly we had jump discontinuity there. Point discontinuity, also called a removable discontinuity. It's a single point that's undefined in the graph, or for piecewise, the two pieces match up to the same point, which is undefined for both pieces. Okay? What that means is they both would be graphed, but both of them would be undefined. Okay? All right. And that's what we had. Infinite discontinuity, jump discontinuity, and point discontinuity. A function is continuous at x equals c if it satisfies the following condition. First of all, the function's got to be defined at c. So if you've got some kind of function going on here and it says x minus 1, and they want you to know if it is continuous at x equals 1, you can stop right there. No, f of c does not exist. It's undefined at 1. I don't have to go anywhere else. It is, the answer would be no, because it's not defined at f of 1. Not defined there. So the answer is no. The function approaches the same y value on the left and right sides of x equals c. So, for instance, that graph that we had at the beginning, it came down here and then was going this way. It was undefined. It was at two different points. This is approaching 1. It's approaching 1 because that point is 0, 1. So the graph is approaching 1 as it goes this way. This graph is approaching 0 from the left. So your answer for that graph from the front is no, it's not going to be continuous. It is approaching 1 from the left and 0 from the right. Okay? 3, the y value that the function approaches from each side is the same thing. So we've got pretty much the issue there. The same y value on the left and right sides of that, and we've got no. That would be how you would discount both places. All right. If you want to use Desmos, it's not hard to do it with here, but you can use Desmos. You would type in the function using f of x. Okay? So we'll go here and follow the directions. We're going to type in the function using f of x. Okay? So, f of x equals, whoops, f of x equals, and this was 3x squared plus 7. So we're going to put that in right here. 3x squared plus 7. Okay. The next thing it says to do on here is to click on the settings and then click on the table. So right here, click on the settings and then click on the table, and it fills in your values right there. Now, if you want to know if it approaches the same number from the left and the right, you're going to do it right here, the table, and you can change the x values to compare. You want to know what's on each side. Well, I have to click it. You want to know what's in each side of 1 because that was the point that it asked for. So, you'll do 1.01, 1.001, 1.001, and then the 0.9's in this direction. You can change the values in the graph to make it happen. Okay? So, to 1, you just have to change your x values. 0.9, 0.99, and 0.999. Okay, whoops. Let's do 4 9s here, and then I'll do 3 9s here. All right, so you can see how this is getting closer and closer and closer to, should have done it the other way, 0.9999 would be the closest one. Okay, 0.999, and then these are getting farther away. Okay, getting closer and closer and closer to 10. It is approaching that. You can also do it on the other one, 1.01. Okay, 1.001. Okay, I should have done the same thing. 1.001, 1.01. That is also approaching 10. So you can do it on both sides using Desmos. Don't have to so much. It is up here, and you can see at 1 it is continuous. You're going to be hitting the same point from the left and right side, so you can see it from the graph. But that's how they have you prove it. All right. Here's an example. Determine whether the function is continuous at the given point. Well, right here we've got y equals x minus 5 over x plus 3. You already know from Unit 1 that x plus 3 cannot equal 0. So x cannot equal negative 3. So at that point right there, no, it is not continuous because the function is undefined at f of negative 3. Whoops, forgot the at. So there's your justification. There's your yes or no answer. It's not continuous. Determine whether the function is continuous at this given point. Negative 2. Oh, forgot to write that. At x equals negative 2, you've got two sides, but it's two sides of the fence, just like when we were doing our piecewise. This side of the fence is 0. This side of the fence is colored in. So I've got negative 2 squared. Negative 2 squared. I need parentheses because if you put it in your calculator without them, you're going to get that that's negative 4, and it's not. Negative 2 squared is 4 plus 2, which is 6. So on this side of the fence, it's negative 2, 6. And on the other side of the fence, it is negative 2, negative 6. So what you've got here is that from the left approaches 6. The right, coming in, approaches negative 6. So the answer would be no. And you could get that off your graph because you've got negative 2, positive 6 up here, which is open, and then negative 2, negative 6 down here, which is closed. They don't approach the same. They don't approach the same point. So that would be no, also discontinuous. All right, I hope that clears it up for you guys, and I will